All right, so let's go ahead and continue on 7.4. In this section, we're going to be calculating the equilibrium constant. Now, we've already looked at how we kind of derive the constant, but the idea here, or the premise, is that we do not know what the value is, and we have to determine that based on values provided for concentrations. All right, so for this particular section, what we want to do is go ahead and do a sample problem. So let's go move this over here to the left. And we'll begin with a sample problem. Let me go ahead and put it on the screen. We're going to deal with a reaction. And so that reaction here, let's move this back up. So the reaction that we're provided is this one here, where we're going to get hydrogen gas. And this is going to react with iodine gas. And so both of these are gases. And this is a reversible reaction that is going to produce hydroiodic acid gas. Now, the very first thing that you'll need to do here is you're going to need to balance this reaction. So if I zoom in on here and we look at these items, notice here we've got 2 hydrogens on the reactant side, but on the left side, or on the product side, we've only got 1 hydrogen. So we're going to have to double that. Coincidentally here, if you look at the iodine, there's 2 iodines here because of the subscript. So that means that we're going to have to two iodines. So the simplest way to resolve this is to go ahead and put a 2 for a coefficient. Now, purposefully, we're just going to put coefficients of 1 and 1 respectively for each of the 2 reactants, which would give us a K expression here of K is equal to the concentration of the HI raised to the 2nd power. And then we're going to divide this by the concentration of the reactants, which are going to be the hydrogen gas raised to the 1 power. I'll purposely put a 1 even though we don't need to. And then the iodine gas as well. And then we'll purposely put a 1 there. Now, up to this point, everybody should be able to get the equilibrium expression. The problem here is that we don't know what the value of K is, but they want us to calculate it. So typically with these kinds of problems, they're going to give you some information. So what information would they give you? Well, typically the given, somewhere in the stem of the problem, they'll provide you concentrations for everything. So let me go ahead and provide those, and then we'll substitute into the expression and solve for K. So if you look at the values that were provided here, the concentration of hydrogen gas is 0.10 molar, iodine gas is 0.2, and the HI, the product, is 1.5 molar. So in these particular types of problems, if they're providing you the concentrations, all you really need to do is make sure your reaction is balanced, go ahead and generate a equilibrium expression, and then take the values for the concentrations provided. Conveniently, these are already in molar, but if they're not, convert it to moles divided by the volume so you can get concentration. But once you got the concentration, go ahead and take the values for each of these components and then plug them into the equation. So just to illustrate here, I'm going to take the 0.010, I'm going to take the value here, and I'm going to go ahead and put it right here in the position for H2. Now, we'll do the same thing for the others, but to clean things up here so we don't get all messy on our screen, I'm going to go ahead and back up that drawing that I did here and just make sure we clean up our canvas here a little bit. And so that's what we'll do. Okay, so nice and cleaned up. And now let's go ahead and substitute into the equation. So now here at the very top here, we'll just continue to the right. The value for HI should be 1.50 molar. And then we'll divide that by the H2, which would be 0.10 molar, multiplied by the concentration of the I2, which in this case is going to be 0.20 molar. Now, the only thing I need to do is for the numerator is, don't forget, the coefficient or the power was 2. So you need to make sure you put that power up here for that particular species for the product. And so we're going to have to square that value. So go ahead and plug this into your calculator, take the 1.5, square it, and then divide it by the product of 0.10 times 0.20, and that should give you the value for K. So let's go ahead and do this off screen. I'll show you the result in a second. All right, so here's the math all the way through. Taking this value here, 1.50, squaring it gives us 2.25. taking the bottom two, multiplying the product is 0.02. If we then take this further, plug it into the calculator, we end up with the value of 112.5. Now notice that there are no units here because all of these units are going to cancel out. So it's important that you understand that. So K values simply provide us a value that we can use to reference to tell us whether reactants are going to be favored or products are going to be favored. And if we want to take the step further here and multiply this or put this into scientific notation, the number here would be 1.13 times 10 to the 2 value. Now, you can see it already here in this value. This number, 112.5, is vastly greater than 1. And so if you want to put it into scientific notation, you can see that the exponent here is a plus 2, which also would confirm it if you had already put the number into scientific notation. So based on this value is going to strongly favor product formation. So you could say that the reaction is strongly favored to produce products. It almost appears like this reaction is going to go to completion, exhausting all amounts of the reactants to form a tremendously high concentration or a tremendously high amount of product. So this is what we do in section 7.4. Just to illustrate an example, what you want to go ahead and continue to do is to continue to practice these things. And remember that all of these values are identified at a very given specific temperature. So whatever temperature this problem was given to us, the K value is true for that given temperature.